Welcome to lecture 11. So we are hopefully going to finish the topic of what we put in general under the chapter of linearity today. And we're almost there. So hopefully not more than the first half of the class today. And then we'll start the discussion on nodal analysis and mesh analysis. And these are just systematic ways of solving circuits. Okay, there isn't really new physics in there. It's a matter of rearranging your algebra a little bit to do things more systematically, so that ultimately, for instance, you could put things into a computer. If you wanted to write a code that would simulate essentially any circuit for you, you could use a systematic approach like that. So we'll start those today. But before that, the main topics that we want to finish with are the wye-delta transformation and the Wheatstone Bridge. And these are not so much, really separate topics, but some specific examples, important examples, but really just some cases of essentially equivalent resistance. Okay, so although you see this list having Thevenin and Norton equivalent and all these things listed together, it doesn't mean that they're all at the same level of conceptual importance, perhaps. But these are still important pieces, and especially the wye-delta transformation is something that gives you additional insight into two-port circuits. So I'd like to, before getting into that, to do a couple of quick examples of equivalent resistance. Okay, so I'll draw a circuit for you. Find the equivalent resistance as a quick exercise here. So between these 2 points, as indicated, I'm interested to know what the equivalent resistance is. And I'm not going to put numbers here. I just want you guys to take a couple of minutes to work through this on your own, assuming these are R1, R2, R3. Okay, so don't worry about doing the actual algebra, but I just want you to look and recognize what's in series with what's in parallel with what, and think about the steps of simplifying the circuit that way. Okay, so just work on it for a minute, and then we'll do it together and then expand the example. Okay, I hope this was enough time for you guys to have a head start, at least, if not finish. But let's see what are the things that we can combine quickly. So just trying to recognize what's in series with what and what's in parallel with what. So these 2 resistors here are in series. I hope you can see that directly. The point of connection between the 2 of them is just shared between just those 2. So there is no other branch separating from them there. And so they have the same current. And so what we did last time to show that 2 resistors in series add up applies here. And you have a similar case here. And another similar case here. So as a first step, maybe you could do all these combinations, and so you would just replace these combinations each with its own equivalent resistance, so the circuit would look simpler. So you would have 1 resistor here, 1 resistor here. Again, I'm not working on numbers, right? So here's 1 resistor, and here's another one. These are connected. And then here we have replaced those with 1. Okay, have I missed anything, or is this good? Is this correct? I hope it's correct. But let me know if you catch something. And maybe it's better if I add a little bit of extra wire here so that we can separate things more easily. So now if I go to the next step, then I have the combination of these two. So these are in parallel now. And these are also in parallel. And remember that what that means is that those two resistors have the same voltage. There's nothing else between them. Or both branches have the same voltage. There's nothing else in either branch. So the combination that we talked about, that the inverse of these resistances add up to give you the inverse of the equivalent resistance, that works here. And incidentally, the inverse of resistance is called conductance. So that's something good to be familiar with terminology. But anyway, so we can then replace each of these combinations with its equivalent. And so we are going to end up with this, something like this. And now the next step may be these three in series. So that's going to give us something like this. And then ultimately these two are in parallel, so you will end up with one resistance that's our equivalent. Now again, remember, in each of these steps, of course, you have to calculate the values. So let's say if these two resistors had the same value, then the equivalent there would have twice that value. Or if the two that are in parallel have the same value, the equivalent of that combination would have half the value. So we're not doing the values. You have the formulas for that there. Okay? Am I right in assuming that you guys did a lot of things like this in first year or high school? That's why I don't want to spend too much time on this. OK, so this is an example. Now I want to do the same example, maybe just add something to it. OK? So let's draw the same thing. So again, find the equivalent resistance. Now work on this on your own. The same thing. Again, we're not concerned about numbers here, but just seeing the different parts that you can combine and simplify in steps to eventually get the equivalent resistance. OK, so let's try to do the same thing as before. Let's start recognizing what's in series with what and what's in parallel with what. So I hope we can see this again, so that those two will just add up to give us one equivalent resistance there. Now, if I have that reducing to one resistance, then I hope we can see that that combination then is in parallel with this. OK, so that's what we had in the previous example also, so I'm not going to repeat that. So that will simplify things a little bit. And then that combination itself will be, this combination itself will be in series with this. So that's going to turn into one resistance. So let me draw the circuit with all those steps implemented, and then we'll see what else we can do. So we turned all those 4 resistors into 1, essentially. Going like that. And then we have this here. And this there, right? So I hope everyone made it as far as this. Now what can we say? What is in series with what? Or in parallel with what? So if I look at, let's start from the top. This top resistor here. Is it in series or in parallel with either one of these? No, it's not. It doesn't share the same current because there is another branch here. Remember, when I'm looking at an equivalent resistance here, it means implicitly that I'm connecting this somewhere else, right? For instance, to an ohm meter. Or I am applying a voltage, measuring the current, and the ratio of the two would be the resistance, right? In general, so this is something I've put in a box, and I'm looking, doing something else to it from here. So there is implicitly a current going into the circuit. So there's a branch here, and then there's these other branches. So this is definitely not in series with either of these. And these are not in parallel because they have different voltages. If I look at any of these resistors, I don't see something that's in series or in parallel with something else, assuming I have designed this example properly. Now, if you guys see something, let me know so that I don't go too far. All right? Nothing in series or parallel? Yeah? So what do I do? So we need a wye-delta transformation. So let's see what I mean by that. This is what we mean. We are looking at a concept of equivalent circuit that's a little maybe extended compared to what we've seen so far. So far, we've looked only at equivalence between 2 circuits that have 2 terminals each, right? So now I want to show the equivalence of 2 circuits that have, you might say 4, or really 3 in this case, terminals. So there is a sense of input and output, if you want. So this is what I mean by a Y. It looks like a Y. And so let's say in general you have a circuit like this with R1, R2, and R3. And you have these wires. So if you put this in a box, and you look from the outside between these points, okay? What this transformation does is it says this is equivalent to something else that looks like this. That looks like a delta, and let's call these RA, RB, and RC. You're saying these 2 circuits, when looked at from the outside, are equivalent as long as, well, there's a relationship between these values of R1, R2, R3, and their delta equivalent RA, RB, RC. And let me write these down for you. You don't need to memorize this, by the way. There's a pattern that you would recognize, but you don't need to memorize it. You need to be able to apply it. So if you had a circuit in the form of that delta with 3 resistances, RA, RB, and RC arranged like that, as far as the outside is concerned between these two sides, you can replace that circuit with something that looks like this Y, with R1, R2, and R3 arranged in that order. So notice the order of these resistors does matter. And then the values of R1, R2, and R3 are given using these. Now let me write it the other way around too. So if you have the Y shape, then if you want to obtain the delta from that, these would be the formulas. And that's the same formulas turned around so that you obtain RA, RB, and RC in terms of R1, R2, and R3. Okay, so, and I hope you recognize the patterns in these formulas. So if you wanted to memorize them, it wouldn't be that difficult, but you don't have to. Okay. There was a question.
I wanted to know, how could you prove this?
How could you prove this? That was going to be my question. Okay. So I'm going to ask you guys next to think a little bit about proving it. I don't need the full algebra again. But I want you guys to think about how we could prove this. The equivalence of these two circuits that are hidden inside the two boxes when looked at from the outside. So consider the fact that I have connected the left side to something, some other circuitry, and the right-hand side to some other circuitry. And so I have a voltage difference on the left-hand side. So let's call this V1. So let's say I have V1 here. And again, when this is connected to something else, and there is a current going in, I1. And then on this side, I have V2 measured between these 2 points. And let's say I2. Equivalence, in this case, means that the same IV relationships should hold if I replace what's inside this box with what's inside that box, right? So I want to have on this other side, again, the same, if connected to the same outside world, I want to have the same V1, I1, and V2, I2. Maybe I'll erase this so that we don't think V1 is equal to V2. But so that the two circuits are supposed to be equivalent. Okay. We're talking about equivalence of these two circuits. So how would I prove this? Right, yeah, so basically you want to analyze each circuit and then whatever result you get, whatever the mathematical relationship that describes the circuit is in each case, you want to say to put them equal and see that that works out if you have these relationships between the resistances. Or you might say this is a way to derive these formulas. So now this is maybe a little more than just one resistance because I have two sides. So if I just look at, so let's say I don't connect anything to the right-hand side, and I just look at the resistance from the left-hand side of this top circuit. Okay, so I connect an ohm meter there. Or I connect a voltage source and measure the current and divide the two. What would I see? So I'm talking about the Y circuit now. If I don't connect anything to its right-hand side, and I try to look at the equivalent resistance from the left, what would I measure if I have not connected anything to the right? R1 plus R3, because R2 is basically just disconnected. It's not going anywhere. There is no current in R2 if it's not connected anywhere. And so basically, R1 and R3 are in series. And by the way, this is a good example also that being in series is not just a matter of what the drawing looks like, right? So again, if I'm not connecting R2 to anything up there, the current I2 is 0. And so R1 and R3 would, in that case, be in series effectively. So from the left, I'd see R1 plus R3. Similarly, if I don't connect anything to the left, and I look at from the right-hand side, I'd see R2 plus R3. So here's something that you can try. This is not the full proof, but here's something you can try at home and see if you are happy with what you get. Now try to look at what you get for the right-hand circuit if you don't connect the right-hand side to anything. Okay? If I don't connect the right-hand side to anything for the right-hand circuit, basically, again, meaning the current I2 is 0, what's the relationship between RA and RC? They're again in series. So you would have RA plus RC there, which is then in parallel with RB. So you can go see if the combination of RA plus RC in parallel with RB, using these formulas, can simplify to R1 plus R3, which is what you saw there, right? So you can see for these special cases if this works out. But maybe that's not enough of a proof, because these are special cases, right? If we wanted to think about this in more general terms, say this is my box. For instance, one way to do this would be to simply put a current source here, right? So if I connected a current source with the current I1 in this direction, and a current source with the current I2 in this direction, and measured the voltage across these current sources. Remember, a current source can have any voltage in theory, right? Within limits in practice, of course, but in theory, any voltage. Well, and I have this resistive network inside, so it's either a Y or delta, okay? Based on all the discussion of linearity that we've had and superposition, you guys would expect something like this, right? V1 to be something times I1 plus something else times I2, correct? Remember how we did superposition. If I have a circuit with, let's say inside I have this Y circuit. Okay, so I have a resistive network with two current sources there, and I'm interested in finding the voltage somewhere in the circuit. Remember with superposition, we said that You can do it for one source at a time and add up the results. And given that this is a linear circuit, you would expect that the dependence of that variable you're interested in, that voltage in this case, V1, the dependence of that on either of these current sources, you would expect it to be a simple proportionality, a linear dependence. This is a linear circuit. Okay? And that's why you can have a relationship like that. So V1 would be something times I1 plus something times I2. And the same thing for V2. Something times I1 plus something times I2. You can call these, let's say, let's call these, maybe to avoid confusion, for now, A11, A12, A21, A22. Okay? These are, now the nature, the dimension of each of these coefficients has to be of the dimension of resistance, right, ohms. And I hope you would agree with me that they would have, they would basically come out of a combination of those three resistances, right, the parameters of the circuit. So this is basically from linearity and superposition. And so these coefficients, so if we call these, let's see, R1, R2, R3 going clockwise, these depend on R1, R2, and R3. So this is basically what determines the behavior of the circuit looking at it from the two sides, from the outside. Okay. Well, now you can do the same thing for the delta. Okay? So do the same thing for the delta shape. I won't draw it again, but basically something that looks similar. And for the same reason of linearity and superposition, you would expect a similar dependence of the voltages on the currents. So let's call that V1 equals, in this case, B11 I1 plus B12 I2, and V2 equals B21 I1 plus B22 I2. So these are those things that would depend on the resistors or the values of the resistors in the delta circuit. So these would depend on RA, RB, RC, or would be written with some combination of RA, RB, and RC. If you want these two circuits to be equivalent, well, they have to have the same relationships, the same IV relationships from the outside. So you have to make sure that A11 equals B11, A12 equals B12, and so on. So now, by requiring that all these A and B coefficients be the same, we will get the wye-delta transform formulas. which ensure that these two circuits have the same IV characteristics when looked at from the outside. That is, they are equivalent. Now that's a little bit of, that's an exercise in algebra because, well, how would you do this? Take the first circuit, put two current sources, I1 and I2 here, and solve the circuit. So you've got a couple of loops, got some branches, write your KVLs and KCLs and everything. Or do it with superposition. Set each current source to 0 at a time, right? So for instance, if I set I2 to 0, I'd have this disconnected. So that would be the special case that I talked about before. And then I'll be able to get the coefficient for V1 with respect to I1 and so on, right? So you can basically solve the circuit, get this A11, all the A's as a function of R1, R2, and R3. Then do the same thing for the next circuit. Do all the B's, write them as a function of RA, RB, and RC, and put all the A's equal to all the B's, the corresponding A's to the corresponding B's, and simplify, and you should get these formulas. You guys can do on your own. Okay? It's a nice exercise for you to do on your own at home. Okay, so now once you do that and you establish this equivalence, you can use this to simplify circuits when you're looking at something like equivalent resistance. Let me now go back to this circuit that we had up here. This is where we got stuck in our example, right? So is there a simplification that I can do from replacing a Y circuit with a delta circuit? Let's just take this. Let's see if this helps me. You see a Y pattern here, right? Now, it might not look like a Y, but from a circuit topology point of view, right? Not the drawing necessarily, but in this case, maybe a T. But the point is you have essentially a star shape, one resistor in each branch of the three branches of the star. OK? Well, if I replace this with a delta, so continuing the example, I have those three resistors, and the three middle ones, if you call these R1, R2, R3, I can replace them with the RA, RB, RC configuration there. So this is what I had around the circuit. Do I have it correctly? And then instead of what I had in the middle, which was, now if I put a delta, I end up with something like this. RA, RB, RC. Is this correct? Can you guys verify that I'm not missing anything? Am I missing something still? So I had 4 other resistors, 1, 2, 3, 4. Yeah, it's good? Yeah, okay. All right, now what do I see? Well, these 2 resistors on the right-hand side, these are in parallel. RC is in parallel with the resistor at the top. And then the combination of those are in series, which then add up. And then that combination is in parallel with RB. And then that combination is in series with this bottom resistor. And then that's in parallel with that left-hand side resistor there. So it does simplify. So notice that what I have done, maybe it's better if I extend this wire a little bit like this. So I have put the box like this. This is the same box that I had. I had my Y shape in, and I have replaced that Y shape with this delta shape. So as far as the outside is concerned, I can do that replacement, and the rest of the circuit wouldn't know. Yeah, so I just want to then simplify those steps that I showed to draw them quickly here. And so I have something like this, then something like this, and then this. And then this will simplify to basically these 2 well, I hope this is easily seen now. So those 2 are in series, and then in parallel with that, and then in series with that. So maybe I don't need to draw that. But if you have difficulty with it, we can talk about it after class. Now, you're saying maybe there's easier ways to do it. And it's true that in general, there isn't a unique way to, if you have a big circuit, and if you get stuck somewhere that makes you think you have to now change a Y to a delta, or vice versa, very often there isn't one unique way of doing it. So you might choose to convert one part of the circuit from a Y to a delta, or the opposite somewhere else. You would still get out of that kind of the situation where you had nothing else to simplify. Okay, and sometimes you might have to do maybe 2 of these in sequence as you are simplifying the circuit. But it basically allows you to get unstuck. So what if I had now more than 3? So let's say I have a connection, a point where I don't have just 3 resistors connected, but 4, right? Maybe that's something good again for people to think about. So think about this at home. Okay, a little exercise. So I basically showed you how to get unstuck if you had a situation where you had 3 resistors connecting, and you didn't have anything in parallel or in series, right? So you had that Y, and you converted it to a delta, and that allowed you to simplify things. What if you had more than 3 things connected like that? See if you can work out the equivalence or whatever simplification you need to do in that case. Okay? Think about this a little bit at home, and if you want, remind me next time we can talk about it. But I think it's a good exercise to think about it. Okay? So you can go home and try to maybe expand this example a little bit so that you think maybe you need something more than just a wye-delta. Okay? Now again, because this concept of equivalent resistance is not that new to you, I don't want to do too much and spend time doing numerical examples and so on. But you can take any of these examples that I've drawn, put some numbers to it, and practice if you feel that you need more practice. Okay? So I want to show you one final thing before we finish with equivalent resistance, and that's this. The Wheatstone Bridge. And this is how it goes. So if you have a circuit like this, And let's say you have R1, R2, R3. Let's go this way. R3, R4, and R5. And this is connected to something else. Let's put a voltage source for now. It doesn't have to be a voltage source. It can be connected to some other circuitry, right? I'm concerned with this shape, this bridge. Well, if I ask you to solve this circuit, first of all, let's say you don't remember anything about equivalent resistance and linearity and superposition and Thevenin and Norton and all these things, wye-delta transform. Ultimately, doesn't matter as far as the circuit solution is concerned. Write your KVLs, KCLs, element relationships, solve the equations, you will get your answer, right? But now that you have some techniques, you can also, so let's say if you wanted to get the equivalent resistance, or for this particular example, if you wanted to see what this current was, well, it would be handy if you could quickly calculate the equivalent resistance and then just divide Vs by that to get the current, right? That would be pretty convenient. Now, if you wanted to do that by using these techniques, the wye-delta transform will come in very handy here, right? Because you can take the top part, the delta there, convert it to a y. So it would look like this. And now, basically, you have, I'll forget about R1, R2, and R5 in black. Consider the blue resistors that I have used to replace the delta with. So now I have this blue resistor in series with R4, and then this other one in series with R3, the combinations of those in parallel, and that combination in series with this other up there. So I can get the equivalent resistance using wye-delta transform. Instead of turning that delta into a y, I could have also done something else, maybe. Could I have transformed a y into a delta? Does anyone recognize a y here? Here's a y, right? Again, the way it looks on paper may not immediately remind you that this is a y, but it is a y. You can go move the wires around, redraw it. And so you could have replaced this with a delta, and then you would have, again, simplified the circuit. You would have a bunch of parallel and series combinations that you could use to do that. So anyway, this circuit we can analyze in multiple ways. What's particularly interesting about this bridge is this. You can show, using essentially any of these things that we've learned, by solving the circuit, you can show that, if you're interested in this, if R1, R3 equals R2, R4, then I5 is 0. So this is a very handy result. If the product of R1 and R3 equals that of R2 and R4, so these are opposing resistors in this circuit, if the product of those are equal, then it's as if the middle branch, that R5, that creates the complications, it's as if that is disconnected. There's no current going through it. Equivalently, there is no voltage drop across it. So these two nodes, the two nodes on the two sides of R5 basically have the same voltage. So this is known as the Wheatstone Bridge. So if you see a circuit that satisfies this condition, if there is no current going through R5, it means we can just remove it and nothing would change in the circuit, right? So that would simplify things greatly. And this is something to look for. This is not just for fun. It also has utility. So this is a type of bridge that's used, for instance, to measure resistance. If you have an unknown resistor, so let's say you have two resistors, R1, R2, and then R3 is a variable resistor, and then R4 is an unknown resistor. So you can put an ammeter in this branch in the middle and change the value of R3 until you measure zero current. And then you have that equation from which you can find your unknown resistor. Okay. And it has advantages compared to, let's say, trying to directly use a voltage source. And now you might say, well, who cares about measuring resistance? But actually many things, many modalities of sensing have to do with measuring resistance. So you have strain resistors, you have chemical and biological sensors, many of which are basically some element that changes its resistance as a response to an external stimulus, such as having some molecules deposited on it. For instance, people, some of you have been asking me about carbon nanotubes, which is what I work with. And one of the applications in the nanotube community, maybe 15, 20 years ago, was sensing. And so you take one small carbon nanotube. These are materials made of carbon with nanoscale diameters. And so if you put a few molecules on a nanotube, you could change its IV characteristics greatly. Okay. So examples of using IV characteristics to detect something that's happening in a system to measure a physical parameter are very common. And so resistance measurement in general, or IV characteristics measurements, are a big deal. And so this is one specific case of resistance measurements. It's something that's also a neat thing, because you can make big circuits that simplify quickly if this condition is met. Again, this is something that you can do prove as an exercise. It would be good practice, again, prove as an exercise. And of course, come talk to me if you have difficulty with it. Okay, I want to mention maybe one final point, and then we will wrap this chapter up for now. And that's going back to the Thevenin equivalent and equivalent resistance. So we've talked about how to find the Thevenin equivalent of a circuit, right? For instance, you could measure or calculate the open circuit voltage or the short circuit current. What if you were not interested in the whole Thevenin equivalent, but only in the Thevenin resistance? What would you do? I mean, you can still do the whole Thevenin thing and just keep V Thevenin in your pocket and show R Thevenin, right? But do you actually need to calculate V Thevenin to be able to calculate R Thevenin? Yeah, so if you have basically a circuit that meets the conditions we've described, which is you have a bunch of independent sources, and you have some dependent sources that have linear relationships, and you have some resistors, linear ohmic resistors. And there is a bunch of sources in the circuit also. If all you want is the Thevenin resistance, well, that's basically just the equivalent resistance of the circuit if you set all sources to 0. Okay? So this is not really anything new, but I just wanted to bring your attention to it, or bring it to your attention. So you have a bunch of voltage sources, you have a bunch of current sources, independent ones. if you replace all the voltage sources with short circuits and all the current sources with open circuits, which means you have set all the independent sources to 0, then whatever equivalent resistance you see between the 2 points of interest, that's your Thevenin resistance. Okay. It really follows from all the discussions we've had before. Just wanted to point it out. Okay, so that's it. That's what I wanted to talk about for now. And we will, of course, kind of make connections back to this concept of linearity and superposition and all these equivalences. And we'll use these in other topics also. But for now, I think it's a good place to start. Let's take a 5-minute break, and then we'll start nodal analysis and mesh analysis. What I'd like to start is the general topic of nodal analysis and mesh analysis. And we will start with nodal analysis today. There are great similarities with mesh analysis. Okay. So let me tell you in a couple of sentences what nodal analysis and mesh analysis are. Compared to what we've seen so far, KVL and KCL, they don't include new physics. Okay, so the laws of the circuits are the same. They are a way of rearranging equations. And in fact, over the past few weeks, whenever you guys have had to deal with a big circuit, I've had people asking, how do I know how to simplify the equations, where to start, how to arrange my variables if I have a system of 10 equations and 10 unknowns? Where do I start? And the answer is to arrange them in a systematic way. And that systematic way, one way of doing it is called nodal analysis. Another way is mesh analysis. And in brief, this is what it consists of. Remember, when you write your KVLs, you have a bunch of voltages, right? All the voltages of the elements. And you have the KVL for each loop. You also write your KCLs, and you have a bunch of currents in there, right? And then you write your element relationships, and typically these give you things like V equals Ri. So you have both voltages and currents. So you have a system of equations that has a bunch of unknowns consisting of some voltages and some currents. Nothing new there, right? As I want to combine these equations and eliminate variables to eventually find one of the variables and then work backward and find everything else, if I rearrange the equations such that I first eliminate all the currents and find all the voltages first, and then using those I find the currents, that's essentially nodal analysis, with a caveat, and we'll talk about that. So not entirely, but more or less. If on the other hand I say, no, I prefer to find currents first and then use the currents to find voltages, that's essentially mesh analysis, again with a caveat. Because the voltages that you use in nodal analysis are not the element voltages, but they are the node voltages. And the currents that you use in mesh analysis, they're not the element currents, but they are what you call the mesh currents. Okay, but that's it. So, and in fact, we have already talked about the concept of node voltage in the past. So, in a way, we really just actually covered nodal analysis, believe it or not. Now I'll write it down, but that's the story. So maybe as a reminder, this is what node voltages were. So if you have an element, doesn't have to be a resistor necessarily. This is some element, and you define some voltage and current for it. So you call this V, and you call this I. And you're putting this in a circuit connecting to a bunch of other things. Imagine this is connected to this branch and some other branch and some other branch. Okay. Each of these nodes that you have in the circuit, you can attribute a voltage value to them. And that value is essentially the the voltage difference between some reference point and this node, or this node and some reference point. So let me write that down formally. So if I call this, let's say, V1 and V2, these are node voltages. Okay. Whereas this V was the actual element voltage with this sign shown. Now, a node voltage is remember we said in the past that it's really voltage difference that actually does something. The same way that if you're in a gravitational field, it's the height difference that does something, right? If you have a flat surface, you put a wheel on it, it won't roll. You need a height difference. In the same way, it's voltage difference that matters. So node voltage is actually a voltage difference, but difference with respect to one specific point that you have chosen as a reference. So it's the voltage difference between a given node and a fixed reference node. This reference node very often is chosen, or the ground of a circuit, if you actually have a physical ground, very often is chosen as reference. And you attribute a value of 0 to it, so that basically a node voltage is a number that represents the difference with that reference point. But the reference that does not have to be ground. Okay, it can be the ground, but the physical ground of a circuit, but it doesn't have to be. Okay. It's wise to say the voltage of the reference is 0, because if you just say, well, the voltage of my reference is 5 volts, you're adding 5 to all your voltages. Why? You know, it's voltage difference that matters. So typically, a physical ground is chosen as reference. Maybe. And then again, typically, the voltage of the reference itself is chosen to be 0, or taken to be 0. But these are not required. They make things sort of more insightful or intuitive and convenient. So once you have defined a reference point somewhere in the circuit, and again, it doesn't have to be a physical ground. You can take any point in the circuit and say that's my reference. And then you measure all the voltage differences with respect to that reference. You basically have the node voltages. And to do that, you would literally take a voltmeter, put one end to that reference, and then put the other end, the high side of the voltmeter, to every node and measure the values. And those are your node voltages. Okay, so we'll see this in examples. Once you have these node voltages, there is a relationship between these node voltages and the element voltages. So looking at this example up there, what is the relationship between lowercase v and the capital V1 and V2, those being the node voltages? It's a difference. Which way? V1 minus V2. And the reason is, you see, the way I have defined the polarity of V, if the left-hand side is at a higher potential, V has to be a positive number, right? So if V1 is a higher number than V2, then V should be positive. So in the example above, element voltage V is equal to V1 minus V2. Node voltages V1 and V2. Notice the direction. Now, the goal of the algorithm of nodal analysis is to write your equations essentially in one step directly in terms of node voltages. That's sort of the goal, so that you don't have all the equations that then you have to simplify. Let's look at it with an example in practice, and then we'll talk about it in more formal ways. So consider this example. Okay, so you wanted to solve this circuit. If I wanted to just do my KVLs and KCLs, so I have this node here, and this node here, and I have this big node down here. So let's give these names. This one is V1, V2, V3, which really is the same as V2. Let's call this I1, which we already know is 2 amps, I2, I3. And so the voltage of this source, let's call this Vs, maybe, the voltage of the current source. And I'll write my KVL here. No idea what's happening. This tablet behaves much better when it's not doing all the other things that I'm asking it to do now, right? Recording at the same time and running the clicker thing and everything. But anyway, so have to be patient with it. All right, so let's write the equations. KVL will give me minus Vs plus V1 plus V2 equals 0, and minus V2 plus V3 equals 0. KCL gives me I1 minus I2 minus I3 equals 0. And I can write that at the node at the bottom. That's the same thing. And also 2 minus I1 equals 0. So I1 is 2, as we see directly there. And then the element relationships, V1 is 8I1, V2 is 3I2, and V3 is 6I3. Okay, so these are all the equations. So the essence of nodal analysis is to eliminate the currents first and find the voltages. So basically, you would take these Ohm's law relationships and put them in your KCLs, and then you would have all your equations in terms of voltages. And then, instead of the voltages, the way I have written them, instead of the element voltages, write them in terms of node voltages. So let's define node voltages. Let's say I take the node at the bottom and call it reference. So I'll say that's 0 volts. Notice this doesn't have to be a physical ground. This is just a circuit on a paper. It also does not have to be the node at the bottom. I could have chosen the node at the top left or at the top right. I guess most of us are more comfortable with having a reference at the bottom, maybe because of our sense of direction with gravity. But it's just more common, but there's nothing about it that you have to do it that way. Now let's also define some other node voltages as needed. So I'll say maybe capital VA and capital VB. So these are some node voltages. And VA is literally the difference between the voltage of that node A and the reference node. So if I had put the low side of my voltmeter here and the high side there, whatever number I measure, that's VA. It can be a positive or negative number, right? Very important to remember. A node voltage can be a positive or negative number. So nodal analysis consists of writing the equations in terms of node voltages. That's it. So let me now first rearrange all the equations in terms of element voltages and then replace those by node voltages. So for nodal analysis, first eliminate the currents to have everything in terms of voltages. In terms of element voltages. So I'll just replace these things. So I have the KCLs, and I'll put the Ohm's law relationships into those. So the first KCL becomes V1 over 8 minus V2 over 3 minus V3 over 6 equals 0. Was V2 over 3. So that's that KCL there. It's not one. And the other KCL is simply 2 minus I1 equals 0. So 2 minus V1 over 8 equals 0. So V1, you really have it directly there. But let's assume this was a more complicated problem, and we'll just continue. And then the KVLs, I'll write them as they are. OK, so same equations as before. So already I have everything in terms of element voltages. Now replace the element voltages in terms of node voltages. So if we go to the circuit, let's look at the connections between these element voltages and node voltages. And remember the definition with the polarity that we had up there. So if you have an element voltage V like that, that's that node voltage minus that node voltage with that direction. OK? So let's apply the same concept here. Vs, what is Vs in terms of node voltages? It's VA minus reference. Look, the way I have chosen the polarity, the plus side. Again, think of it this way. If Vs was a positive number, let's say if this was 5, it means in that case that the top side is more positive than the bottom side, right? And so VA has to be a positive value. So Vs is simply VA minus 0, minus the reference, which we've chosen to call 0. So Vs is simply VA. You might say VA minus 0 minus reference, so that's just VA. What is V1? It's like the example I had. V1, little v1 is capital VA minus capital VB. V2 and V3, which turn out to be equal, are just VB minus 0. And so if we put these in the equations that we have up there, what do we get? Try it. So take these little v's in terms of the big v's and put them in the 4 equations that we had up there, KVL and KCL. See what you get. Yeah, I'll do it in parallel with you guys. So the first one is minus Vs plus V1 plus V2 equals 0. So put in KV, KCL. So minus Vs, which is minus VA, plus V1 plus V2. Equals 0. The second equation is minus V2 plus V3 equals 0. The third equation is V1 over 8 minus V2 over 3. So V1 over 8 is just VA minus VB over 8 minus V2 over 3 minus V3 over 6 equals 0. And the final equation was 2 minus V1 over 8 equals 0. Okay? Now let's just work on these equations and see what we get. What's the next step? Simplify. Carry out the algebra work. So what do I get from the first equation? Minus VA plus VA minus VB plus VB equals 0. That doesn't seem to be very insightful, right? Minus VA plus VA minus VB plus VB equals 0. That's 0 equals 0. How about the second equation? Minus VB plus VB equals 0. Also nothing maybe too special. 0 equals 0. Again, proven. The third equation. So I have VA times 1 over 8 minus VB times a bunch of things, right? So I have 1 over 8 times VA minus 1 over 8 plus 1 over 3 plus 1 over 6 times VB equals 0. And finally, I have, maybe rearranging, 1 over 8 times VA plus, minus 1 over 8 times VB equals 2. So what happened? Two equations, two unknowns. VA and VB. You can find them quite easily from this. What happened to the first equations? Was this some trick? The first equations were KVL, and I just showed that KVL was led to 0 equals 0. That should be pretty disturbing. I mean, we've been using KVL for a month, solving circuits with it. You actually see it works. It gives you information. It wasn't supposed to be 0 equals 0. What happened there? You know, I just got my node analysis equation. Why did the KVLs become trivial? Now, maybe I'll remind you of what I said maybe in the first lecture or second lecture when I briefly talked about these node voltages. You can probably find this in your notes. I said KVL is nothing but a manifestation or another representation of the fact that voltage is a well-defined quantity, that you can say each node has a well-defined voltage. If you do that, indeed, as you said, if you write the element voltages in terms of node voltages, KVL will have automatically been implied. So it's not that KVL does not exist or is trivial or obsolete. Not at all. The way KVL entered our equation was by this very definition up here. This thing that I said, this little v equals v1 minus v2 is KVL. Because imagine, this v1 is the voltage difference between this point and some reference here. So think of this as a loop. I have some reference point here, a v1 increase in voltage, then a little v drop in voltage, then a v2 drop in voltage. That's your KVL. Minus v1 plus v plus v2 equals 0. Or v equals v1 minus v2. That is KVL. This is where you enter KVL into your system. So this is essentially your KVL. So by choosing to work with node voltages instead of element voltages, you have automatically written your KVLs without having to do it explicitly. And that's what happened. So I didn't need to write my KVLs. The KCLs, on the other hand, I did need to write. And I got these equations. And my variables are node voltages. So by writing nodal analysis, I have essentially ended up with a smaller system of equations. Rather than having all the element voltages and currents, I have just a few node voltages. Okay, so this not surprising because KVL was already implied in the concept of element versus node voltage. Okay, this is really what happened. Your KVLs are automatically taken care of, and so all you have to do is to write your KCLs and do so in terms of the node voltages. Excuse me. So if you look at the circuit here, what happens is the KCL at this node A at the top left, there is just telling me 2 amps equals that current I1. Well, from Ohm's law, the current I1 is V1 by 8, but V1 itself is big VA minus big VB, and that's this, basically, VA minus VB divided by 8 equals 2. And a similar situation for the other node. I1, which is this little V1, which is VA minus VB by 8, equals I2, which is VB by 3, plus I3, which is VB by 6. So in fact, you could have, with a little bit of experience, you could have written these two equations, the KCLs, directly in terms of VA and VB without having to go through all those steps. Now, you might say for this little circuit like this, it's not a big deal. You can do it directly with your KVLs and KCLs. But imagine if you have a circuit with many elements, and you want to have a systematic recipe so that you can write a computer code to solve any circuit. This would be very handy, because you can look at these equations now and look at the coefficients. There are things that you recognize here. You see 8, 3, and 6. Those are the values of the resistances in the circuit. And the way they appear in these equations is not accidental. There is actually a pattern in this. And so I invite you to go home and take a look at this and see if you recognize some patterns. Because next time I'll write down what that pattern is so that you have a recipe. But this is it. So this is, we'll of course talk a lot more about it and do examples too, but this is the essence. So till next time then, thank you.